Lecture 213, Velocity Transformations. We've spent several lectures looking at the Lorentz transformations, so here they are again. We want to now derive expressions for how velocities transform when we're in two different reference frames. So we imagine here's the ground frame, we'll call this the O frame. Here's the moving platform, we'll call this the O prime frame. And then there are two observers, and they're each watching a third object move through space. So the person on the ground frame will see that this object has a velocity u. The person on the moving platform will see it has a velocity u prime. The simplest way to find the transformation equations is to go back to the definition of average velocity. So ux is going to be just the change in the position over the change in time according to measurements made in the unprimed frame. And ux prime is going to be delta x prime divided by delta t prime. So both the x and the t have to be in the same reference frame. We'll use the displacement equations to calculate what delta x and delta t are in terms of the prime coordinates. So for delta x, we'll take this equation and plug it in. For delta t, we'll take this one and plug it in. Notice that the gammas are going to cancel out. If we divide the top and the bottom of each by delta t prime, we'll have delta x prime over delta t prime. This delta t prime will just go away when we're dividing through by it. We've got a gamma that's gone away. This delta t prime goes to 1. And then this delta x prime will be delta x prime over delta t prime. So we're just dividing top and bottom by delta t prime there. Based on our definition on the previous page, delta x prime over delta t prime is just ux prime. And that goes here and here. So that's it. That was our whole derivation. We're going to do the same thing for components that are perpendicular to the motion, either uy or ux. So here's uy, it's delta y over delta t. We plug in for delta t here. Delta y, remember, is just the same as delta y prime. So we just can write delta y as delta y prime there. Do the same thing, divide top and bottom by delta t prime. We get delta y prime over delta t prime. This turns into a 1, and then we get delta x prime over delta t prime for that term. Notice that the gammas don't cancel here because there's no gamma on the top this time. So we're going to write that 1 over gamma is just square root of 1 minus b squared over c squared. Delta y prime over delta t prime turns into uy prime. And then this delta x prime over delta t prime is ux prime. So that's it. That's the equation for a perpendicular component. You'd find the exact same thing if you plugged in, if you wanted to solve for uz. So uz would just be uz prime times all this stuff. Okay, so here we go. Here's our set of transformation equations. You can do it the other way around too. So you could solve for the primed velocities in terms of the unprimed velocities. You just get a change of sign here and here. Then you get a change of sign on the bottom, change of sign on the bottom. Remember that in the regular Lorentz transformations with coordinates, it was only the component along the direction of motion that was transformed. The others were just, y is equal to y prime, z is equal to z prime. That doesn't happen here. All three coordinates actually undergo a transformation when you're looking at velocities, and that's because of time dilation. So it's the time dilation factor that has to be taken into account in this case. Okay, here's a simple example. Olivia drives past Oscar at 90% the speed of light. A sports car drives past Olivia at 90% the speed of light relative to her. how fast is a sports car going relative to Oscar? So the first question is who wants to be the primed frame and who wants to be the unprimed frame? It doesn't matter. It's slightly simpler to think about if Olivia is in the prime frame because the velocity that shows up in the gamma factor is always the velocity of the prime framed relative to the unprimed frame. So we're given that Olivia is traveling at 90% the speed of light relative to Oscar, so it makes sense that she is the prime frame, Oscar is the unprimed frame. But you could do it the other way around. Because Olivia is measuring the speed of the sports car, ux prime is going to be 90% the speed of light, and then we're trying to solve for ux, unprimed. So use the velocity addition formula where we're given v ux prime. We're trying to solve for ux. There it is. Plug in the values. So 0.9 plus 0.9 is 1.9 on the top, but then you're dividing by this factor on the bottom. You get 0.9945c. So you're getting something closer to the speed of light, but it isn't greater than the speed of light. We'll see later on that Einstein's theory of relativity says that you can never go faster than the speed of light, no matter what reference frame you're in. So we've seen that. So again, the sports car is going 90% the speed of light relative to Olivia. It's only going a little bit faster, it seems, relative to Oscar. So 99.45% the speed of light. So here's a slightly different variation on this problem. Suppose that Olivia now turns her headlights on. She's still going 90% the speed of light relative to Oscar. If Olivia turns her headlights on, she sees the speed of the light going out from her headlights as just c. The question is Oscar going to also see that the speed of the light is c? Right. So we want to just make sure that the velocity transformation equations are consistent with Einstein's postulate that the speed of light is constant for everyone. So it should turn out to be c. So we go back to our equation that we used before. We're now going to plug in that ux prime is c. So here and here is c, and then velocity is 0.9c, 0.9c. So when you do that, you get a 1.9c on the top. On the bottom, you get 1.9. You get 1.9. So the 1.9s cancel, and you get c. So this is good. This says that both observers see the same speed of light c. Here's another example. This is historically significant. This is one of the experiments that help support the theory of special relativity. This is an aberration of starlight. So it says, assume the Earth's orbital motion around the sun is perpendicular to the line connecting the Earth and a distant star. So here we have a distant star up here. Here's our motion through space like this. And in the frame of reference of the star, the light is coming straight perpendicularly down towards the Earth. Okay. So this is like so the Earth is directly under the star in the frame of reference of the star. The question is, what is the apparent angle of the light from the star as seen in the moving reference frame of the Earth? So it's going to be angled in slightly towards the Earth like this. We want to find that angle theta, and in order to find that, we need to find the components of the velocity of light from the Earth's reference frame. So we're trying to find ux prime and uy prime. Now, remember, the speed of light is constant for everyone. That means that if you figured out the magnitude of u prime, that's going to be c. So ux prime squared plus uy prime squared square root, that would just be c. But the components are going to be different. So we're going to use the velocity addition formula. The velocity of the moving reference frame is going to be 29.8 meters per second. In the unprimed frame, uy is just going to be c, ux will be 0, right, because it's coming straight down. And so we're trying to find these velocity components. So it'll be helpful, it'll simplify the calculations a little bit to write v as a fraction of the speed of light. So if you take 29,800 meters per second divided by the speed of light, so that's going to be 9.9 times 10 to the negative fifth times c. So a pretty small fraction of the speed of light. Okay, so we have the velocity addition formula for the x component of the velocity. Remember that ux is 0 since the light wave is coming straight down. So ux is 0 down here. So this whole term on the bottom goes away, and ux is 0. So ux prime is just minus v. So ux prime is just going to be 29.8 meters per second. Or minus 9.9 times 10 to the negative fifth c. Okay. We plug in now for the y component in the prime frame. Ux down here is 0, so this denominator is just 1. So uy prime is going to be ui times the square root of 1 minus v squared over c squared. Plug in for v, and you get that it's 0.999999951 c, so very close to the speed of light in the y direction. In fact, for the calculation, you could probably just round this off to c, but we'll keep it like this for now. Okay, let's just check to make sure that the magnitude of the speed of light in the Earth's frame really is c. So we do this by plugging in, we can actually just plug in our expression. So ux prime was negative v, but squared. And then uy prime was square root of c squared minus v squared. So we square the square root. So the square root goes away, and then we have a v squared minus v squared. So we have the square root of c squared. So in fact, it checks out to be c. So that's good. That's just like a reality check to make sure our component expressions were on the right track. Okay, so now we can figure out the angle just from the arctangent. So that this angle would be the arctangent of ux prime divided by uy prime. So we take the arctangent of basically c divided by 9.9 times 10 to the negative fifth c. And that works out to be 0.0057 degrees. If we convert that to arc seconds, where 1 arc second, well, 1 degree is equal to 3,600 arc seconds. It's a very small unit of angular measure that astronomers use. Turns out to be 20 arc seconds. The limit of the resolution of the human eye is around 60 arc seconds, 1 minute. So this is actually a pretty big shift. I mean, you could almost, like maybe, I don't know, like owls or something could potentially see this shift if they had something to compare it to. So this is actually a fairly significant shift that you could almost see with the unaided eye. You could certainly measure this with telescopes very easily. And they did. So James Bradley, back in the 1700s, actually measured this change in the position of stars perpendicular to the Earth's motion, and he confirmed that it was around 20 arc seconds for stars perpendicular to our motion. So one question is this different than what classical physics would predict? And the answer is, well, slightly. So this is the result that we just found, that when we're on the Earth, the star appears to be, even though the star is physically perpendicular to our direction of motion, it appears to be slightly forward as we're moving through space. So the velocity of starlight coming towards us is, of course, c. It's a constant. This is the velocity of us as we're moving through space. And then this a perpendicular component to the velocity is square root of c squared minus v squared. So in special relativity, the sine of this angle, you could think of it as v over c. In Galilean relativity, we simply add the velocity of light perpendicular along the y-axis to the horizontal component with v, and we find out that the diagonal here, the hypotenuse, the magnitude of the velocity is going to be the square root of v squared plus c squared. So this is a value greater than c, which is, again, is prohibited by special relativity. So in this case, it's the tangent of that angle, which is going to be v over c instead of the sine of the angle. But since this angle is so tiny, only 20 arcseconds, it's very, very difficult to distinguish these two scenarios. So certainly they didn't do it back when Bradley was making this observation. He couldn't distinguish Galilean relativity from special relativity. Of course, special relativity didn't exist back then, so he wasn't trying to. So because this angle theta is so small, only 20 arcseconds, it's very difficult to distinguish these two possibilities. So the aberration of starlight occurs both in special relativity and in Galilean relativity, but the exact mathematical form is slightly different. Okay, so that's it for addition of velocities.